Thank you for introductions. Thank you for kind invitation. I would like to somehow continue with the problem of the standard model and tell you something what is related with the new physics beyond the standard model. So I will speak about neutrino oscillations, about the neutrino double beta decay, about the neutrino masses, and I will discuss the present status of experiment looking for neutrino double beta decay, discuss related problems with many different mechanisms of this process. I will touch also the problem of the nuclear matrix element for this process, related experiments to determine the effective axial coupling constant and nuclear matrix elements, and also address that there is some new physics which can be looked for into neutrino double beta decay. So we know that standard model is very successful, but not perfect. You know, the cosmological observation, we have the problem with dark energy, dark matter, asymmetry of matter and antimatter, what cannot be explained with standard model. But we already know there is some new physics beyond the standard model because neutrino observations were observed in different experiments registering atmospheric neutrinos from accelerators, from sun, from reactors, from the Earth, and so on. So we have some already evidence about new physics beyond the standard model due to small masses of neutrinos. And neutrino is a puzzle. It is the only elementary particle which basic properties we don't know. We know only that there are only neutrinos entering the interactions, there are neutrino propagating in space, there is some unitary transformation between them, that there are three flavors, and we don't know the nature. Is neutrino own anti-particle because it's neutral? There is such possibility. It can be Dirac or Majorana type if it's own antiparticle. We don't know much about CP violation in neutrino sector, about magnetic moment, about some additional neutrinos, sterile neutrinos. But the main subject is just nature, mass hierarchy, CP properties, and sterile neutrinos currently. So you see, this problem of Majorana neutrinos was already proposed in 1937. That's a very long time ago. The possibility of neutrino oscillation was suggested in 1957. At that time, no flavor was known, so there were some rumors that Ray Davis registered neutrinos from reactor, but from reactor comes only antineutrinos. So the only explanation what was thinking about that time was Bruno Pontecorvo, just oscillation into the sterile neutrinos. Something, and it requires also Majorana, the neutrino Majorana particles. An explanation of small masses is generally accepted and supported, is, for example, by Steve Weinberg, that we can construct 5-dimensional operator related with new physics beyond the standard model. So in the standard model, we have only the 4-dimensional operators. I will come later also to this problem. So we can, for three flavors neutrino and 3 massive neutrinos, we can construct Pontecorvo-Dirac-Majorana mixing matrix, which is a product of these 3 rotations, and it depends on 3 angles and 1 CP phase in this transformation. And the global fit of all neutrino experiment indicate the possibility, because only 2 mass squared, the small one like from the sun, the big one like from the atmospheric neutron is measured, that we can, so we need additional information to construct mass spectrum of neutrinos, which can be, when we put small difference up or down, it can be inverted normal hierarchy. So the global fit currently are more in favor of the normal hierarchy. So we have rather precise information about this mixing matrix, about all on mixing angles, and some already indicated that the violation of CP in the sector of neutrinos with Dirac phase. So this formalism of neutrino oscillations, which is used for analysis, is just, I would say, it's quantum mechanical. So it is considered that we have propagation of plane wave. It is formalism which was proposed a long time ago by Gribov and Pontecorvo, and we can, in this case, we have some source, we have at the distance else, we have some detectors. So it is like three processes: production of neutrinos, propagation, and absorption of neutrinos. And this for such a the production rate then depends on the energy distribution of neutrons in the source, propagation, the distance L, and the cross section. So it is like the people discuss it today, and the oscillation probability, as we are working only with plane wave, is given here. We look a little bit different on this problem. Actually, we were inspired that we are working a long time with neutron zone beta decay. So we look at this process like neutrinos double beta decay with real neutrinos. So what in that case? In that case, this approach that was developed for some time by Walter Grimus from Vienna. So he was assuming we have just one Feynman diagram. We have just one this Feynman diagram. It is just one Feynman diagram, what we have. Let's discuss it in that way. So we have just S matrix, which we have source, production. We have two vertices, x1, x2, one associated with the source, second with detector, and we have a lepton current, which includes also the propagator of neutrino. In that case, as we have real neutrino, they propagate from the source to the detector. From the propagator, we just cut this inverse term, and then just standard approach, because there is a then we integrate, take only this part over the time component we have here, x1, x2, 0. As it is the second of the process, one gives us energy conservation for the whole process, and second integration gives us energy denominator. This is the second of the process. That, like in neutron double beta decay, the same. Then we get this from the neutron propagation, we got this term. Here we have pole in the denominator. We can integrate what gives us actually energy conservation in the source and detector, defining neutrino energy. And it can be simplified because there is a big distance between the source and detector. And further, we can even write amplitude, which contains full energy and momentum conservation. There is Lorentz invariant, and it contains the two hadron currents and these lepton currents, where enter the neutrino momenta. So we derive the master formula. It is somehow like Fermi golden rule for the second order process with real particle propagating. And we make normalization because we are plane waves. And so we have these momentum conservations here. And we normalize all these plane waves separately for the source and detector because they are produced in source and detector. Of course, all this normalization goes out, factors, and we get the we apply this formalism for a process of pion decay, an oscillation muon to electron neutron, and absorption of electron neutron by neutron. So in the standard approach, when we have just two separate processes and propagation of neutron by plane wave, we get the expected results like it is given here. So we have separately energy distribution in the source, probability for oscillations, and just cross-section for the absorption of neutrinos. if we use our master formula, we get some additional term here. We have to calculate traces. So there is some entanglement. So these two processes are connected. You cannot be considered as individual. That's the new point here. And of course, as neutrino masses are small, we practically reproduce the origin formula expression. So make it sense. So thinking about it, of course, we address this approach also to the oscillation of neutrinos to antineutrinos. You see, long time ago, Giulio Rakach, he proposed to prove the Majorana nature of neutrinos by detecting real neutrinos. Not like neutrinos of beta decay, we have virtual neutrinos with real neutrinos. So actually, we have again these three processes, but we have in between oscillation neutrino to antineutrino. And with our formalism, this in our amplitude, we get instead of the momentum, just mass of neutrino is expected due to projection. So we end up with such probability, which contains what is the difference in this term, mass over energy, which is not present in standard oscillations. So then we end up with expression as we see. So these oscillations of neutron to antineutron can be given as just some effective taking the L equals 0. We get just effective Majorana mass divided by energy squared. And this effective Majorana mass is also relevant for neutrons, double beta decay. It's not showing pointer more. I don't know why. So it's indicated there. And you see there is so-called dangerous region where we can have, for normal hierarchy, there can be full cancellations. It can be 0. But in the case of oscillations to neutron, antineutron, it is given, this region can be clearly determined. But if we come back to this oscillation probability, which depends on the L, putting L equals 0, we get this quantity. So let's analyze this quantity as distance of L, and then we find that even if there is cancellation in this region, for some L over E, we can avoid these cancellations. So we are always moving in this region, which is allowed for the effective Majorana mass, because this region is given by the arbitrary values of Majorana CP paces. And we can, for example, taking the value of the lattice neutrino 20 millielectron volts. So the upper value is changing always in the blue color. And, you have it.
This is just the point.
Oh, great. Well done. So is by blue color, and from here, from the spin, we can go. So therefore, we are thinking about some astrophysical possibilities for such an oscillation, or maybe we need to construct a huge power nuclear reactor, not only 3 gigawatts, and put some detector very close to see for such an effect. So we are thinking about that possibility. So coming back to the Majorana nature of neutrinos, so this 5-dimensional operator can be constructed when we have in the standard model only left-handed currents, so coupled to Higgs. After symmetry breaking, we create the vacuum expectation value, and this operator is associated with some length of number violating scale. We don't know what it is, but if it is the good scale, we get the correct masses about what can be in the below electron volt range, maybe milli-electron volt range. So in that case, there is a possibility to observe neutrinos double beta decay. That means this process, which was proposed by Fourier. There are about 50 nuclear system, 56, which can be studied this process, for which the transition from even to odd nuclei is energetically forbidden, and the only open channel is by change of charge by 2 units. So people, to see this process, are looking for a peak at the end of the spectra of the sum energy of 2 electrons. So they take in this process all the energy. The recall is negligible beyond the energy resolution in this process and so on. So the half-life for such a process depends on this effective mass of Majorana neutrinos, depends on some Axion coupling constant, on the nuclear matrix and kinematic factor, and these effective masses depends on 3 masses, 2 mixing angles, and 2 Majorana phases. So there are these 2 possibilities for so-called inverted spectrum and normal spectrum. So we can plot, because we are missing the additional information of neutrino mass to say something about the absolute scale of neutrino masses. And this additional information can come from cosmology, which is measuring the sum of the masses of neutrinos, or it can come from observation of kinematic observation of neutrino mass in tritium beta decay. But so cosmology restricts already this region for the lightest neutrino mass. This effective mass is a function of the lightest neutrino mass as indicated here, the so-called inverted spectrum, and this is the normal spectrum. There is this cancellation. So there are many nuclear systems favorable for to study or to look for a signal of neutrino beta decay. The most favored are given here. Most preferable are those with largest skew value and natural abundance. It's you see by tellurium is 34%. Yes. So there are different techniques: bolometer, trecocalorimeter, TPC chambers. It depends on the isotopes. There is a list of the experiment for different isotopes. And here is given the sensitivity. They include effective mass of Majorana neutrinos larger as this quantity already. So that means we are already in this region. We are some experiment of this regional inverted hierarchy. So if there is inverted hierarchy, we will see maybe within few years, and neutrinos are Majorana, we will see within few years signal. But okay, other experiment which also will look for the hierarchy of neutrinos, like Juno, reactor neutrino experiment, or some accelerator experiment in preparation is just June. So they will maybe June, maybe early will tell something about it, about the possibility of inverted hierarchy. So just only a few experiments. Most favorite is Kamlanzen in Japan, in Kamioka mine. So there is a combined results of then Kamlanzen 400 and 800. So they use xenon, and they got the half-life of is given here of 10 to 26, about 2.3. There is experiment in preparation. It is first Legend 200 and Legend 1000. It's just unification of Gerda Majorana experiment, Gerda at Gran-Sasso, Majorana in Homestake at present, but this in construction. Maybe next year we will have some data, Legend 200. And in the perspective how it will be sensitive. So you see that we can even come to the region of 10 to 28 years, so this experiment will be sensitive also to the normal hierarchy of neutrino masses. Another favorable experiment is Cupid. It is just bolometer in which one can identify alpha and gamma signal And again, it is proposed one-ton experiment. So maybe till now it was the experiment of the except this Kamlanzen of tens of kilograms. So now we are coming to the scale of 1 ton kilograms neutronal beta decay experiment. And here are the perspective of these 3 experiments, which sensitivity in respect to effective molecular mass it is expected they will reach. Of course, it depends also on the nuclear matrix element. It depends also on the what is the value of effective axial coupling constant and so on. So, but nevertheless, there are good perspectives in this sense. But the mechanism can be more complicated, that we have not only exchange of 3 light neutrinos, very light, but we can have additional neutrinos, so-called sterile, which within the interpretation of this 5-dimensional operator in great unified theories, we have the seesaw mechanism. It can be with heavy right-handed neutral fermion, or just with, it can be also with triplet Higgs, seesaw 1, 2, and so on. And we don't know where is this lepton number volatility scale. It can be any, from KV Fermi energy level, TeV. Hey, okay, excellent. So it can be any. So in that case, there are also discussed scenarios that, for example, we have 3 light and 1 heavy neutrino, sterile neutrino. And they couple only due to mixing. And in that case, the half-life is more complex, so we have to sum over all neutrinos. And in the case of heavier neutrino, we cannot already neglect the mass of the neutrino in the denominator. We add in that case just on nuclear matrix elements which depend on the neutrino mass. And there are 2 limitations. In the case of, we can neglect light neutrino mass mechanism. So the matrix element for this is given here. For heavy neutrino exchange, in limiting case, we can write as it is now here. And this formalism, it was found that one can use so-called interpolating formula which connect these 2 extreme cases, very light and very heavy additional neutrino. And the corresponding matrix also behaves like the neutron propagator when we have in the numerator mass and in the denominator mass squared in combination with the exchange momenta, which is typically about 100 MeV in nucleus. So then one can present this plot when we have mixing of this heavy neutrino as independent of the mass of the heavy neutrino, and we see the neutronal beta decay can exclude everything what is below and can exclude even better as many laboratory accelerator experiments. Yes. It will just use this interpolating formula. We can even extend model the further, so we can have 3 light, 3 heavy neutrinos, and we can, in addition to the left-handed interaction, we can have right-handed interactions because we have a left trisymmetric model. So it is a significant simplification of the mixing matrix. Then the effective lepton number parameter with this interpolating formula will be more complex. So it will not include only the effective neutron mass, which can be identified with the first element of the neutron mass matrix. And so then we will be not able to distinguish contribution from light and heavy neutrino exchange. It is mostly because this quantity entering there is given by ratio of these 2 matrix elements. Practically in each nuclear structure model is practically unsensitive to the A of the decaying nucleus. One would like to avoid this simplification with 6x6 matrix when you have 15 mixing angles, 15 phases. So just using the seesaw structures, let's consider that we have just light and heavy sector determined by the two unitary transformation, and this additional parameter comes due to seesaw structure. And in this case, we found, just taking unitarity condition, we find out that this heavy neutron sector will be just Hermitian conjugate of the PMNS matrix. So that means what we call before the Dirac phase, if it is this structure, it will enter also in neutron gamma beta decay, this contribution. Then we can estimate just the effective mass parameter for this process related with this heavy neutrino exchange. We need additional information about light and heavy neutron masses. We can use just this inverse proportionality, or just proportional for just to make some analysis. And we found that this quantity can be even in the range of which will be studied by this and next generation neutron beta decay experiment. So for these two different scenarios, inverse proportionality of mass, light and heavy masses, and proportional, will be able to say something about the dominance of light and heavy neutrino contribution. But of course, we need some additional information. Is from processes that accelerators, if possible. Now, so it was just assumed that neutron masses are generated by 5-dimensional operator, and there is so-called Schechter-Waller theorem saying that independent what is the mechanism of this process, we can always connect because we are changing two d quark to two u quarks, and we can correct this d with neutrinos and getting in this way a small, but it is a radiative correction to the Majorana neutrino mass. So in that case, we are proving that neutrinos are Majorana particles. So there can be also other mechanisms when only 5-dimensional higher. So is it not necessary that we should follow this blue and red region, but everything below can be identified with some new mechanism. So in addition to 5-dimensional operator, we can construct 7-dimensional operator or 9-dimensional operator, which will contribute to this process in which the lepton number is changed by 2 units. We discussed the possibility of 7-dimensional operator, which is given E, 2 leptons, lepton doublets, quark doublet, quark singlet, coupled with Higgs. After spontaneous symmetry breaking, also after the chiral symmetry breaking, also we already create the quark condensate, and we get for the neutron masses so-called the seesaw scenario. And in this seesaw scenario, already when we have this lepton number virtual scale is Tavy scale, that's which is addressed at the LHC, so we can have correct neutrino masses, so below electron volts or below of the order of tens of milli-electron volts, tens and 100 milli-electron volts. In the case of the 7-dimensional operator, we can even predict the masses of neutrinos. It is because then the dominant contribution will be this mechanism when we have vertex due to this 7-dimensional operator, and in addition we will also mechanism with exchange of light neutrinos. So making constraints on these interactions from the current half-life limit, we find out that to accommodate both together, we have to be in this region, only normal hierarchy, and in this narrow region, there is the cancellation. And this region is very narrow. It allows us to predict out the masses of neutrinos in what should be observed in tritium beta decay experiment, and what should be observed in cosmology for this given scenario. There's also another interesting mechanism, just opposite to the seesaw, that we have quasi-Dirac neutrinos. Quasi-Dirac neutrino means that we have 6 neutrinos, and 2 by par are with close quasi-degenerate masses. And if you say quasi-Dirac, because in limit case, when the splitting is 0, we can generate Dirac neutrino. From 2 Majorana neutrino, we compose a Dirac neutrino. And again, here is the problem of these 50 mixing angles, 50 phases. So, but we can write this unitary matrix which is entering here as product of these 3 matrices, right, for real neutrino mixing, for sterile neutrino mixing, and some additional matrix X, which has off-diagonal element. We assume they are small because we would like to be close to diagonalization of the mass term in the case of Dirac neutrino. In the case of Dirac neutrino, MR equals 0, and Dirac mass term is diagonalized by 2 unitary transform measures, which can be U and V. And we already know that U matrix has structure of a P-S matrix. So we can suggest that we are close to the Dirac neutrino case with only very small splitting being like this Majorana mass. So we can write the oscillations of neutrinos. We find the additional term due to small mass Majorana, which are entering here. So all these are additional terms. So we can study by neutrino oscillations these neutrinos. And for oscillation of antineutrino, we get the standard contribution, a contribution proportional to this epsilon squared. And effect for tritium would be practically 0, it's very small. And from cosmology, we get just what would be in the case of Dirac neutrinos. And we assumed that we are playing with this quantity of splitting by assuming 3 sigma accuracy of the oscillation from Juno. And in that case, we got prediction for effective mass, Majorana mass, which is proportional to epsilon, 30 millielectron for normal ordering, and 1 millielectron for inverse ordering of neutrinos. So it is just the 3 sigma region. You see for these small quantities which are given here, practically no change. But for on a large distancing, like it will be in Juno experiment, they have a detector 53 kilometers from the 2 reactors. This small difference already would change, especially in inverted ordering of neutron masses, the spectrum. So even from sun, it can be even more sensitive. So we are just analyzing constraints on the quasi-Dirac neutrino from this, from sun and from reactor associated with Juno. Of course, one can look for lepton number violation also with experiments at LHC. So one assuming PP collision, one can produce right-handed vector boson, and then is decayed on heavy neutral fermion, which then decay and produce 2 jets. And people are looking for such process, and even already exclude some region as the mass of the right-handed vector boson and mass of this heavy fermion. This is excluded, what is given here. And here is the exclusion from neutrinos about beta decay, everything what is below. So there is also possibility that at LHC, one can observe this process, even earlier with neutrons of beta decay, but there is still some space for it. Okay, so just only small comments. Humanity is solving problems sometimes for a long period. I would just point your attention that the Fermat wrote this theorem, and it was proved only after 50 years by Andrew Wiles, that it doesn't work for n larger than 2, yes? We are only 85 years from that Majorana wrote this paper about Majorana neutrinos, and he disappeared. So there is a chance that this experiment will solve this problem, but there is also a possibility that effective mass is much smaller, and then we have no technology for it now. We don't know how long it can take the time. Nevertheless, on this, people are optimistic, and we would like to be prepared for observation, and people are calculating nuclear matrix elements. So long time ago, there were these astonishing diagrams saying that there is large difference in calculation. There are only two types of calculation, nuclear matrix element, but in between, all the best nuclear many-body approaches were used or addressed to this problem, because this matrix element can be not related with any other process, and the matrix element have to be calculated. So as is a nuclear physics, you need approximations. You need just choose some nuclear structure models. You have some many-body approximation. Each model has some advantages, disadvantages, mostly depending on the how large model space they cover, or it is just pure mean field approximation, or how much the ground state correlation I take into account. And there is some promising development with ab initio approaches, but it works only for light nuclei now. And there is also problem with the effective operator, and also it should be addressed that for double beta decay, this ground state of initial and final nuclei belong to two different isospin and spin isospin multiplet. So we need to violate isospin or spin isospin in nucleus, and there should be sensitivity to it to get the correct value. So here are the current situation with nuclear matrix element for light neutrino exchange and heavy neutrino exchange. And you see the spread is factor of 2. Even for heavy neutrons, there are larger differences. May be some models have not enough large model space to discuss also transitions through higher multipolarities. So additional problem appeared recently that it was found that to ensure the renormalizability of the amplitude for changing 2 neutron to 2 proton, they found there should be some additional term added, so-called delta term, and this term, delta contact term, and this term gives contributions comparable with the previous nuclear matrix element. So it is now well understood whether using different approaches we go through intermediate nucleus, or just when you write compare it with this effective field theory, in which we write, instead of summing over intermediate state, we write all possible transition operator 2, 3, and more, whether it is included or not. So this is now discussed. We need also additional experiment to understand what is happening, especially we would like to know strengths from final nucleus to the intermediate nucleus, or from initial. So therefore, processes like beta decay, electron capture, 2 neutron double beta decay, important charge exchange, pion double charge exchange reactions, and so on, single charge exchange reaction, and heavy ion double charge exchange reactions. So 2 neutron double beta decay was already measured. The matrix elements for this process are taken from the measured half-life and given here. So we see much larger spread of the nuclear matrix element for 2 neutron double beta decays for neutron double beta decay. What is the reason for it? Some people were thinking there should be some proportionality between both types of matrix element, but it seems not to be the case. There are some discussion that even with single low-lying 1+ transition in this mode, one can good reproduce the half-life of this process. But there is a discussion whether how important are the transitions to higher states, where we have also gamma resonance and so on. But experiments just like NEMO 3 and so on, qubit, exclude the possibility of the highest state. The most important is transition to gamma resonance. Some improvements we made also for description of this process. We pay for it with additional matrix element, but the ratio of this matrix element with power, because we can take into account the lepton energies in the denominators, is the second of the process. If it is taken into account, one calculation depends on this ratio, some kinematical factor, and in that case the question is what is the value of this ratio of these two matrix elements, because it depends also on the effective GA, like it is indicated in QRPA, and now this value will be published for SUPIT soon. So in this way, giving some prediction with GA, what is crucial, you see, half-life of this process is GA to the fourth power. Therefore, it is so important. It is just, see, this experiment has already 10,000 and some already 1 million events data set, and so very good description of two neutrino mode, and can see already this effect, which depends for different GA, like it is indicated here. The GA was also studied. There is some Nature paper. The author with an effective field theory, the author is claiming that if one considers meson exchange currents and three body forces, in that case there is no need for quenching of GA. So GA should be like for free nucleon or 1.27 or maybe a little bit less, about 1. Good test for this is also muon capture to understand GA, because we have a lot of measured half-life, and there's also interested in this experiment. They measured a lot of strengths from the final nucleus to the intermediate nucleus, also by higher energies. And the calculation shows that the measured half-lives are practically close to the unquenched value. So for small model space, large model space, and with it is for GA 1.0 and for large model space for GA 1.0 and 1.27. What's the good message for the experiment? New initiatives are just in some laboratories like RIKEN, in Catania, when they would like to measure double charge exchange nuclear transition initialized by heavy ion. So one can go from final nucleus to initial nucleus or opposite with this type of reactions. And what is interesting, there are possibilities for other nuclear transitions, and they can distinguish all these transitions and measure everything. And what is needed, that one need from the all measured strengths for the transition to the ground states, and the transitions are already fixed. So you see the small quantity. Now there is an upgrade of setup, and they will have much stronger beam, and they expect that they will better predict this quantity, and it is really a very good test for nuclear matrix element calculation, and can decide which nuclear matrix element are the correct one. So we are on the way with nuclear matrix element, problem of GA. Everything was helping this DCAE reaction, contact resistance problem, muon capture. We are not well understanding SU4 symmetry. Two-neutrino beta decay is not easy to describe. Only two model can do it through intermediate nuclear shell model and QRPA. Now, shortly about the new physics, which can be studied as byproduct in this experiment, or maybe as main product in some of them. So there are many effects like decay processes with emission of Majoron, decay 1 or 2 or more, when can be so-called Lorentz invariance violation, or even study the bosonic nature of neutrinos, because we need at least system of two neutrinos to conclude about it. And all these processes have different this shape factor. So we are looking for a bump in such distribution with no for to neutron double beta decay. We can extend Lagrangian with left-right-handed currents, with right-handed currents, and assuming such mass of heavy neutron MEV range. And so in that way, we will have, like it is here, additional contribution, and we are looking for bump due to these contributions. And the sensitivity of two neutron double beta decay experiment to exclude in this range are practically the best from all studied with accelerators or with single beta decay. Good technology for this is trecocalorimeter, like supernova experiment. We should start working next year. It is just shown here, and this is my last slide. Something what is apparent, that the problem of neutrino physics cannot be solved with artificial intelligence. Only we, you, me, can contribute to it. So let's do what we can. Thank you for your attention.